Hi, I'm Tommaso, PhD student at Graz University of Technology.
And I'm Daniel, also a PhD student at the Graz University of Technology.
Welcome to Bridge the Gap, the physics-oriented podcast,
in which we give insights into various research topics and the life of scientists.
And by the way, if you want to contact us, you can drop a line to our email address, bridgethegap@tugraz.at. Hey Daniel.
Hey Tommaso.
Do you know what a pigment is?
I think it's somehow related to colors, no?
True enough, yes. The formal definition goes like this. A pigment is a powder used to add color or change visual appearance.
That sounds very interesting.
Sounds very interesting, right? Yes. This will be a topic for today's episode. And on this note, do you know what a pigment's favorite complement is?
Oh no, it seems like it's time for your infamous joke session again.
Yeah.
What a pigment's favorite complement is? I have no idea.
Well, of course, you're looking so saturated today.
Amazing joke as always. Could you maybe explain so me and our listeners understand?
Yeah, saturation is the intensity of a color, you know, so saturated, it's like, yeah, the pigment is super bright today.
Right, okay.
Okay, what about this one? Why did the pigment feel misunderstood?
Pigment felt misunderstood. I have no idea what the reason may be.
There were too many shades to its personality.
Also very exciting one.
But I mean, jokes apart.
We asked some of our listeners what they know about colors and pigments, and here are some of their answers.
The electromagnetic spectrum is the frequency representation of different type of signals in the time domain. What are colors are different frequencies, and they might be more known for the visible range, where somewhere in the terahertz may be named also as optical signals.
So the electromagnetic spectrum is something I naturally associate with colors, and it spans from like short wavelengths to long wavelengths and is divided into sections considering their frequency. And colors, on the other hand, are just like small part of the spectrum that the human eye can see, which ranges from like 400 to 690 nanometers.
So the electromagnetic spectrum would be a kind of way to sort electromagnetic waves by wavelength and general attributes, and colors are just one part of that spectrum, which is the part which is most like the sun emits the most.
So today we're going to talk about colors, pigments, and other shades of physics. In order to introduce the topic, I wanted to start from an article by Nassau from 1980, which was published on Scientific American. So the article starts like this, quote, "What makes the ruby red? Why is the emerald green? When light passes through a ruby, it emerges with a disproportionate share of longer wavelengths, which the eye recognizes as red. Light passing through an emerald acquires a different distribution of wavelengths, which are perceived as green." Now, all of this is quite fascinating, but we need some general understanding for it. And with us to discuss about this and other topics, Anna Galler, a researcher at Graz University of Technology. So, Anna, can you please introduce yourself and welcome.
Yeah, thank you for having me here at your podcast. Today we wanted to talk about pigment materials. That's one class of materials that I have done research on during my postdoctoral stay at the Polytechnique in Paris, mainly. That was my FWF Schrödinger project, which was on novel inorganic pigment materials.
And so what exactly did you research there? Or why is it interesting to research inorganic pigment materials?
Yeah, so you can imagine that the need for pigments is always there, since everything which is colored in daily life needs some colorant, and one possibility are pigment materials. And nowadays, I mean, we have a good selection of pigment materials, but many of the ones which are used today, some of them are a bit toxic or not environmentally friendly. For example, the red and yellow pigment materials that are used a lot are like cadmium sulfide and cadmium selenide pigments. And the blue, there is like a cobalt blue, and cadmium and cobalt are not so healthy. So there exist research efforts to search for new, more environmentally benign pigment materials. and less toxic compounds.
And why is this challenging to find, or what is the difficult part there?
The difficult part, so often pigments, they are discovered by accident sometimes. So there is like a new blue pigment material that I was doing research on. And this was discovered, it's like hexagonal yttrium indium O3, where some of the indium is replaced by manganese. And then the material shows a very brilliant blue color. And actually this was discovered by accident, I think in 2009 at Oregon State University. And the chemists, the researchers there were investigating this material, but for other physical reasons. But then they discovered, oh, this material has a very nice blue color. And so started to do research also on that and see if this material could be used as a pigment material. And actually nowadays it's used as a new blue pigment material. But with the computational capabilities that we have nowadays, it would be nice to do this search for pigment materials a bit more systematically. So to simulate the material on the computer beforehand, right? To see if I take a certain crystal structure, what color would this material have in the end? And can we kind of design a pigment material on the computer before we start to synthesize it in the lab? So this would be the goal also of the research that I did, to develop computational techniques to simulate the optical properties of potential new pigment materials on the computer. And the first step there is to take some pigment materials where we already know, so they are already known which color they have, and to understand why do they have this color. And then you can develop like a computational, a theoretical methodology to also predict the color for other compounds.
Mm-hmm. I have a twofold question, I would say. So, for example, can we take a step back and you can tell us like briefly what a pigment is exactly? And also, what's the difference between the coloration? So like what does change in order for them to have different colors?
Yeah. Inorganic pigment materials are like fine powders of colored materials. So if we go back a long time, people used pigments to color, the walls. Mm-hmm. And what people used back then, so there was no like modern chemistry, of course, but there exist minerals which are colored, and you can make those minerals into powders and use them as pigment materials. And those natural minerals which were used a lot, for example, are natural ochres, like that's iron oxides. And those iron oxides, they can have colors, broad palette from yellow, brown to red. Those were used a lot. Or there were also much more rare and precious pigment materials like lapis lazuli, which is also a natural mineral, which has a very nice blue color, and that one was very precious, and it can also be made into a powder and used as a pigment material. So this is like some examples from ancient times. But then with the advent of modern chemistry, those pigments, people also try to synthesize pigments in the lab. You can start from something very simple, like if some material absorbs all the light, that's like kind of a black body, then the material appears black. While if all the light is reflected, all the visible light is reflected, then it appears white. That's, for example, like snow. In snow, you have a lot of reflection. That's why snow appears white. But then if you have materials that selectively absorb or reflect the visible wavelengths, then you can have color. For example, if you have a material, a semiconductor, for example, which has a band gap of around, I think, 1.6 to 1.7 eV, that means that only the long wavelengths of the visible light, which is the red wavelengths, they are reflected, while all other wavelengths are absorbed. And this makes the material appear red. So because it's mainly the red part of the spectrum which is reflected, or which is not absorbed from the white incident light.
That sounds very straightforward. So then what is the difficulty in simulating these materials?
I mean, you can imagine if you have a solid material, you have a crystal structure. The crystal structure is usually regular, but you have a lot of atoms or ions in there and a lot of electrons. And it's about to know if a certain wavelength gets absorbed or not. It's about the interaction between the electrons and the light. And the electrons in a material, due to quantum mechanics, they have certain energies which are allowed and others which are not allowed. So in atoms, you may know, atoms have very distinct energy levels. For example, sodium atoms, if you evaporate sodium atoms, then they will glow. And the glow is yellow. Mm-hmm. That's very characteristic of these atoms. Mm-hmm. And it's similar for solid materials, but there it's much more complicated because it's not single atoms which glow, but the electrons in a material, they have certain energy levels, energy bands, which are allowed. And in order to really simulate those energy bands, complicated numerical methods are necessary.
Now, going back to your research that you mentioned before, you said you investigated this particular material which was accidentally discovered in 2009, right?
Yeah, that was one of the pigment materials that I investigated, yes.
Mm-hmm, that was one. And if I remember correctly, in there you showed that according to some concentration of one element, you had different colors. So then what were the conclusions in that work? How could you relate how the concentration changed the emission or the reflection of some wavelength?
Yeah, so we wanted to know what the cause of the blue color in this yttrium, indium, manganese blue is.
Thanks for saying the name again, because I forgot.
Yeah, so it has this very bright blue color, but only if you replace some of the indium atoms and only a very small fraction with manganese. So there is like a 5% manganese in this material. And then the material has a very brilliant blue color. And we wanted to understand, so what's the reason for this blue coloration? So we did a simulation. So I computed the electronic structure of this material and investigated like the optical response of the material. So what happens if white light is incident on the pigment material? And it turned out that in this material, it's the manganese 3D electrons and optical transitions between the energetic states of these manganese 3D electrons, which give the blue coloration to the pigment material. And it's actually often the case that it's transition metal oxides, transition metal elements or rare earth elements which give a color to pigment materials. Because in transition metal elements, you have partially filled 3D shells. So not all electrons take part in the bonds when you form a solid with those elements, but you have some free, more or less, not completely free, but you have some electrons which are not part of the, for example, ionic bonds or covalent bonds. And those electrons, they have excited energy levels which are in the visible region because they are not so strongly bound, so they are not in the ultraviolet. And then you can have optical transitions between those 3D energy levels, which are exactly in the optical range. And it turns out that this material, only the blue light is reflected, while all other wavelengths are absorbed. It's mainly, and it's then these manganese impurities and their 3D electrons, which give the blue coloration to this material. And what's also what plays a very important role is it's not only the kind of the elements, like in this case manganese, but also the crystalline environment, which atoms, which ions are around these manganese impurities, in this case, in this material, and in which kind of configuration. So if it's octahedra and so on, because it's called the crystal field. It's the electric field which is produced by the surrounding ions. And this crystal field, it can influence quite a lot the energy levels of those active electrons which give the color. So it can be that in one material, for example, manganese gives a blue color, but in another host material, it could give a red color.
And how well could you then reproduce the experimental results in your simulations? Is there something that's to be improved, or did it work very nicely?
Actually, I developed like a computational approach already before for another class of pigment materials, which were rare earth-based pigment materials. And that was like a series of red-yellow pigment materials. And along studying those materials, I developed a computational approach. And it turned out that that approach also worked very well for this blue pigment material. So actually for those pigment materials, it was working pretty well. Then, of course, it can be when it is like impurities, like transition metal impurities or earth impurities, giving the color, it can become pretty complicated because you can imagine if you have a impurity in a regular host material, you need large supercells to really simulate this material. And that's a challenge, I would say.
You said something along the lines, white light impinging on a material, right? And all these some selected wavelengths being reflected. So now if we take another step back, what is white light exactly?
So white light is like a mixture of all optical wavelengths. So sunlight is white light. And it's basically it includes the entire electromagnetic spectrum from red to violet. So then if you have wavelengths which are beyond, which are even longer, then you are in the infrared, which is not visible anymore. And if you go to even shorter wavelengths than violet, then you are in the ultraviolet. But in this optical range, which is between around, I think, 400 and 700 nanometers, the electromagnetic spectrum is the one of visible light.
So you said you investigate more generally magnetic and optical materials, right?
Yeah.
So is there also some kind of interplay between those two effects? Like are optical properties also affected by magnetic properties or vice versa?
There is for sure like a relation, since it's in both cases, it's about the electrons in a material. And it's the electrons which interact with the light, and it's also the electrons which carry a spin and which can have a magnetic moment. So there is a fundamental link, since it's about the electrons.
Did you ever investigate something?
So actually, those pigment materials which I investigated, so these rare earth fluorosulfides and these blue pigment materials, they are all non-magnetic.
But like you never investigate specifically this... Okay, we don't
you mean something like that magnetism changes the color of something?
Yes, or...
So I'm not aware.
Okay,
yeah.
just curious.
Do you maybe want to comment on other aspects of your research? Because you're pretty involved in a lot of projects. So, for example, what are the other fields of your expertise?
Yeah, so maybe since Daniel was asking a bit about magnetism, so I also did research also on magnetic materials, in particular on rare earth permanent magnets. So there is also the connection between the materials. So kind of the class of materials that I mainly investigate are strongly correlated materials.
What does it mean?
These are materials where the interaction between the electrons plays an important role, and the interaction between the electrons can lead to new phenomena. So like, for example, in a so-called Mott isolator, it means that the interaction between the electrons can make the material insulating. And also like other very fascinating phases, so-called quantum phases, can emerge from this electron-electron interaction, like superconductivity, for example. But I wanted to talk about
No, you just
magnets.
said, you said like correlated materials. Mostly you investigated correlated materials, right?
Yes.
Okay, so yeah.
Yeah, and this other class, also not pigments, which I investigated, were rare earth permanent magnets. There it's also about the rare earth elements, like in these rare earth pigment materials. And you might know that in every electrical engine, you need a permanent magnet. And there are actually the conventional permanent magnets, which are used nowadays, is this neodymium iron boron magnets. They are good magnets, but you need heavy and expensive rare earth. So there exist efforts to search for new materials, like cheaper materials, more environmentally friendly materials. So similar motivation to the pigment materials. And there I investigated cerium-based hard magnets. So how good can cerium-based hard magnets get? So in those magnets, you want to have a high magnetization. But a high magnetization, for example, you also have in iron. But iron is not a hard magnetic material, but a soft one. And hard magnetic means that the magnetization does not switch, so that it sticks in a certain uniaxial direction in the material. So it stays permanently there and it does not switch.
So when will we have cerium-based magnets?
Actually, there are companies which are already working on those cerium-based magnets. Actually, it turns out that cerium by itself is not as good as those heavy rare earth elements like terbium and dysprosium. But you can make some kind of grain engineering. You need to imagine such a magnet in the end is not a plain bulk material where there's one regular crystal and nothing else, but it has grains. And you can do some grain engineering, like put cerium, which is not as good as some other rare earth, like kind of in the center of the grains. And there are companies which are already doing that.
The research you do, it's more direction applied, right? Like at least more than we do.
Yeah.
So,
but not only applied. Yeah,
yes, okay. Part of the research you do.
Yeah.
The simulations you did, have they sparked some experimental insights? Also like some...
Yeah. So actually the project that I talked about the rare earth permanent magnet, that was a direct collaboration with material scientists, with experimentalists. So in that case, it was a joint project. So I did the simulations and I predicted the magnetic anisotropy of those cerium-based magnets. And then my colleagues, they are at TU Darmstadt, and they really synthesized the materials in their lab and they measured the anisotropy. So there was this direct connection. And also for the pigment materials, for those rare earth fluorosulfides in France, I was collaborating with solid state chemists or experimental solid state chemists in Bordeaux who are really synthesizing those pigment materials.
Do you think at some point this will also become industrial? Like, will it go
Actually, some of those, like the blue pigment material that I talked about, so this yttrium, indium, manganese blue, it has already become industrial. So it's already used in paint these days. And also I think of the red pigment materials, so this cerium fluorosulfide is also already used industrially. So
that's amazing. I mean, that shows how from a sort of very abstract computational simulation you get to something that's really applied then, right?
Yeah, and this is also something that I'm really fascinated by or interested in. Yeah.
I guess something that never occurred to us.
No.
Will also occur to you. It's really nice, I think, this moment when you simulate something and then it matches experiments, or when you can explain some experimental observation with your theory. So this is like a really nice moment.
No,
I think
it's nice to see you so excited about it, because for us it's probably uncharted territory.
For sure.
But you also need you need to develop the methods in order to arrive at that point. So for example, during my PhD, I was also mainly doing methods development. So I developed a new method for those strongly correlated materials, right? So if you don't have these methods, if you don't do this basic research of developing the methods, you will never be able to apply it to anything useful.
There's hope. Okay, and on this note, I thank you again, Anna, and see you next time.
Thank you.
Thanks for listening.
And hear you next time.
And by the way,
if you want to contact us, just send a mail to bridgethegap@tugraz.at.